Cool. Great, we'll resume our afternoon session with the talk from Dempsey from Princeton University, who will talk about this work, paper preparation. Joined with me. So I will keep very impartial. Please go ahead.
Great. Yeah. Thanks, Igor, and thanks to the organizers for the invitation. Yeah. So thanks. I'm excited to talk about some. Oh, I'm sorry. Yeah. Let me do that. Yeah. Okay. Does that work? Okay. Great. All right. Yeah. Thank you for the invitation to talk about this. I'm excited to share some fun work with an ongoing collaboration with Igor and Silviu and Ben Sogard and Bernardo Zahn, who are both here on the two-flavor Schwinger model. Okay. So first, some overview of why 2D gauge theories are interesting. We've heard about some of them today already. In our community, they form great models of confinement. Confinement is the default behavior in 2 dimensions. The Coulomb potential grows as the separation. And they also have some interesting deconfining transitions when there are massless fermions in the game, although there are many interesting subtleties with that story. And they're a nice model for symmetries, ordinary and generalized, and their anomalies. They're also of interest in the condensed matter community. They form great targets for numerical tensor network methods. These are cases where we have a lot of exact and non-trivial results. And largely owing to the fact that there is no dynamical gluon degree of freedom in 2 dimensions, it can be integrated out, and these models can be represented often in terms of spin chains that are familiar targets for these kinds of methods. And maybe the most interesting thing, which I will not talk about at all, is that these are also experimentally realizable. People using cold atoms and optical lattices can simulate these the long-range potentials that show up in these theories and actually simulate some of these with real atoms. So in this talk, I'll be focused on one of the simplest possible cases, the Schwinger model, which is a U1 gauge theory coupled to some fermions. And there'll be a theta term as well, which I'll talk about at length later on. And so the 2 questions I want to focus on, one is how can we realize it most faithfully on the lattice, which will involve some discussion. And then we'll use that most faithful lattice representation to learn some new things about its physics in the continuum. Okay, so I'll mostly be interested in 2 flavors, but I'll start with a discussion of 1 flavor to build up some of the story. So we're going to build a Hamiltonian lattice formulation. So we'll start with the Hamiltonian. We have 3 terms. One is the gauge kinetic term coming from this E, which is conjugate to the gauge field, and it's shifted by theta over 2 pi. So we should think of theta here as just a background electric field that shifts all the electric fields. And then we have fermion, kinetic, and mass terms. And very importantly, the gauge invariance implies 2 things for us. One is the local Gauss law that says that this electric field is going to change depending on the fermion number density. There can be normal ordering ambiguities on the right, which I'll come to later. And second, large gauge transformations tell us that these E of x's should be integer valued, but then the effective electric field, E of x plus theta over 2 pi, we can shift with theta. So to put this on the lattice, we'll go back to an idea from Banks, Susskind, and Koga from 1976, which is to take the 2 component fermions and stagger those components on the even and odd sides of the lattice. So we'll have a lattice where the even components, pi0, pi2, pi4, correspond to the upper components of this fermion, and the odd sites correspond to the lower components. And then on the links, as usual, we have the electric field, the gauge field. So let's think about how we can take that Hamiltonian and turn it into a lattice Hamiltonian. The gauge kinetic term is fairly simple. It turns into a sum of these LNs, which are our lattice operators for the electric field, again, shifted by theta over 2 pi. We have a fermion kinetic term. And importantly, we're going to choose the gamma matrices such that the gamma 5 that appears here is sigma 1, such that this term is going to link an upper component to a lower component. And that's something that looks like linking two adjacent components on our lattice. So we get something that looks like a fermion hopping term on our staggered fermion lattice. And finally, the mass term is going to be just represented, since gamma 0 now is forced to be sigma 3 by this choice. We have a minus 1 to the n term, a minus 1 to the n factor in this sum for the mass term. And again, probably most important, the gauge invariance condition. Here's where those normal ordering ambiguities come in. Ln minus Ln minus 1, which is the change dielectric field, is going to be related to the fermion number density, but there's a shift we have to include. And there's some choice here, but we need to have a shift. And so we choose to put it by minus 1 on the odd sites. And so this is what we need to impose on the lattice to guarantee gauge invariance and to have product conjugation symmetry. Okay, so all that is just to say that the literature, I should have said, yeah, we have some parameter here we put in front of this sum, which you might expect would just be the mass, and in most of the literature it is. We claim that this should actually be shifted by something proportional to the lattice spacing. And the reason for that is symmetry. So we want to preserve some of the anomalous axial symmetry. And so, recall there's this axial rotation, e to the I alpha gamma 5 times the fermions, and it's not preserved in the quantum theory. It has this anomalous current whose divergence is related to the effective electric field. We could write this as a divergence of a gauge non-invariant term and try to imagine sort of a gauge non-invariant conserved operator. The effect of which, if we look at what this term is, it's epsilon times f mu nu. So if we try to act with this operator, really what we're doing is adding this term that looks like the theta term. So we're going to end up shifting theta. And so at the end of the day, when we can show that these axial rotations are going to change theta by 2 alpha and rotate put a phase factor in front of our mass. And so this is a well-known continuum story. And for most values of alpha, we shouldn't really expect to see this on the lattice. It would do something pretty funky. But for alpha equals pi over 2, it's rather special. The axial rotation will just interchange the upper and lower components of the fermion. And since we have this staggered lattice formulation, we could really imagine doing that on the lattice by something as simple as just a one-site translation. So one-site translation down this lattice is going to take chi0 to chi1 to chi2, and remember these are upper, lower components. So this is something that looks a lot like what could be the axial rotation by pi over 2. So let's see if we can make that story more explicit. If we look at our lattice Hamiltonian, you could almost imagine, this term is just a sum, this term is just a sum. These things are going to be just fine under a one-site translation. It's the minus 1 to the n that would seem to be our problem. And we could almost get away with it just by flipping the coefficient of that term. But not quite, because of our meddling kid, the Gauss law, which is not explicitly not invariant under a one-site translation. And so if we want to make this into a symmetry, we have to be sure to preserve this Gauss law for our gauge invariance. So let's do that. So if we now try to do this one-site translation, send the fermions to the next site over, this will change the QNs by a shift of minus 1 to the n. These are related to the Gauss law, and so we have to shift the LNs appropriately to maintain the Gauss law. So we get another shift by 1, in this case on even sites. And now we see what this is going to start to change the Hamiltonian that we wrote before. So the LNs that appear in the gauge kinetic term, because of this preservation of the Gauss law, now need to shift. And we can rewrite that shifted sum of ln squared in this sort of suggestive way, where we now have theta shifted by pi, as we should have for an axial rotation, and then an additional term with this alternating sum of the ln's. If we then use the Gauss law one more time, this alternating sum of ln's becomes an alternating sum of chi-n dagger chi-n. That's just the mass term. So at the end of the day, what we've recovered is the same Hamiltonian, except for a shift of theta by pi and a shifted mass, which is possibly unexpected.
Kind of the limit a equals 0, right? terms which are union A could be added from the very beginning.
That's exactly right. Yeah. So if you're taking the continuum limit of your lattice, you can add anything times A to the mass, and you'll get the same limit. That's right. Yeah. So you will have the same continuum limit. I'm going to show that it gets there a lot faster. You're right. I'll show that in just a moment. Right. So yeah, in brief summary, in the continuum, an axial rotation by pi over 2 is going to shift theta by pi and negate the mass. On the lattice, by following our node, we've found that a one-site translation has almost these properties, except it shifts the lattice mass, it negates the lattice mass and also shifts it. And so this suggests an identification of the lattice mass with the mass by this d squared a over 8. And right, so this will have the same continuum limit, but it might be improved on a finite lattice, which I'll show in a moment. Okay, so let's do a first test case with sort of a rather simple quantity, the expectation value of the effective electric field in the ground state. So for m equals 0, the continuum axial symmetry sets this to 0. This quantity is just 0. But the lattice doesn't know about the continuum axial symmetry, right? So the lattice can give us a non-zero quantity that in the a equals 0 limit brings us back to 0. Restoring this little bit of the axial symmetry takes away some of what could be the dependence on the lattice. We could, for a generic, non-shifted mass, we could have had cosine theta, cosine 2 theta, cosine 3 theta terms when we compute this on the lattice, and we've just killed off alternating terms. So we can see the effect of that now on the lattice. I'll show a couple plots like this, but so this one we've as a function of theta, we've computed this expectation of the expected electric field. The triangles are without the mass shift. And so the gray triangles are for a very small lattice of 4 sites. The darker triangles are a slightly larger lattice of 10 sites. And they are getting there to the right answer, to 0, but they're really taking the scenic route. The circles are with the mass shift. And we can see, first of all, this exact result that it's only a cosine 2 theta dependence and higher, even frequencies that show up. And then even by the time we have 10 sites, we're almost very close to 0 already. So this is a huge improvement over the unshifted model. I should emphasize 10 sites is something you can really simulate on your laptop. This corresponds to diagonalizing a matrix of a few thousand dimensions. Actually not too taxing. And we've graphically improved what that can do for this observable. And if we turn on a mass, now it doesn't have to be 0, but still the circle points that have the mass shift are going to follow the result from mass perturbation theory much more closely. So we've again improved the behavior. And just in case computing 0 wasn't so impressive, we can try to compute this more complicated observable. So from Bosanization on a circle, we have this exact result for the from Hetrick and Hosotani for the expectation value of this mass operator psi bar psi. It's a very complicated expression, but we can just try to see, we can plot this to compare to what the lattice gives us. And again, the triangles are sort of getting there, but they're really still quite far off with these small lattices. With the mass shift, we really track this quantity quite well as a function of the circle length. This is again encouraging for what we can do with the mass shifted lattice approach. Okay. So now that we've finished these sort of test cases where there are exact known results, I want to look at something where we really need the lattice to even have a hope of seeing what happens. So I want to talk about the phase transition for a Schwinger model at theta equals pi. So to motivate this, if we think about the theory on a circle being in some fixed electric field background, we can do some pair creation to shift the value of the electric field by 1. And so we can think of this as sort of descending to a minimizer of the effective electric field squared. That minimizer is unique except when theta equals pi. Then, of course, we can have the plus or the minus 1/2 electric field backgrounds. And so there, you can imagine there might be 2 phases here. One with this very small m, where this same process is going to be fluctuating between these 2 vacua, the plus 1/2 and minus 1/2, two states, plus 1/2 and minus 1/2 states. And so we have a single vacuum. For large mass, though, those fluctuations should eventually freeze out. And so we expect this to become 2 ground states, each with a non-zero expectation value of the squared electric energy density. So something has to happen in between, and we expect there to be a second order phase transition for some critical MC. And a simple question we can ask and try to answer on the lattice is, what is the value of this critical mass? Okay. So this has been asked and answered before without the mass shift. So way back in the 80s, using exact diagonalization on the same order of, say, 10 sites without the mass shift, Hammer and friends found a critical mass of 0.325 plus or minus a bit. We did their exact same calculation with the mass shift and get roughly another digit of precision. Now it's 0.335 with some uncertainty. A great tool, which I wish I could speak more about, but I'll just, a lot of those details is DMRG or tensor network methods. These are tools developed largely in the condensed matter community, but they allow for extremely efficient extraction of the lowest eigenstates from some of these types of models. We'll think, just sort of a magic tool that lets us go from 10 sites to close to 1,000 sites at the lattice, and so we can do a much better precision. This again has been done before without the mass shift, and there it was shown that the critical mass is 0.3335 with some uncertainty in that last digit. At this point, it is tempting to think that perhaps this is a rational number we all know and love. I'm so sorry, but in one of the greater disappointments of the recent past, we computed this to one more digit of precision and showed that in fact the error bar just tightened around this 0.3335 value, and it is not 1/3. But that curiosity aside, the nice thing about this is that we have an extremely sort of precise way of extracting these critical points in these models. And so we want to see what we can use that for in other cases. Let me just describe that method real quick. What we did in this case is a little bit different from those other 3 cases, although we did it their way as well. But perhaps the most efficient way we've been able to find is to look at the entanglement entropy on the lattice. So we take our one-dimensional lattice of these fermion sites, split it into 2 sections, and calculate the von Neumann entanglement entropy of 1/2. And it's known that if we're at a critical point, right, that this is going to scale universally as the central charge, in this case divided by 6, times the logarithm of the system size. And so what we can do is compute the ground states on the lattice, extract these entanglement entropies for various subsystem sizes, and use that to extract an estimate of the central charge. And so we can see what happens when we do that for the one flavor case. I hope I said before, but these models are this transition we're looking at is expected to be in the 2D Ising universality class, and so it should have central charge 1/2. These estimates actually go well above 1/2 and back down, but this is really a sort of a red herring. What we should be looking for is not the point where they're maximized, but the point where they seem to be, as we increase the number of lattice sites, the point where they seem to be stable and scale invariant. This is the point that should correspond to the critical point. And we see that this is very nicely getting to C equals 1/2 and is near this 0.33 critical value. So by doing this very carefully for many sizes of the lattice and for many lattice spacings, we can extrapolate the continuum value of the space. So those are the tools. Now I want to apply it to the 2-flavor model. And so let me remind some differences between the 2-flavor and the 1-flavor Schwinger model. With 1 flavor at m equals 0, all we have is the Schwinger boson. There's no massless sector. For 2 flavors, we still have the Schwinger boson, but then there's also going to be a leftover degree of freedom, which forms C equals 1 conformal sector, which is given by the SU2 level 1 WZW model. So this is distinct massless theory for sure. A small change in the tools, the mass shift ends up having twice its value, now A/4 instead of A/8, but it's very much the same idea. It restores a notion of the axial symmetry. And the best part is that the axial symmetry for 2 flavors can be made a true symmetry. Right? Before we had to shift theta by pi, so we're really relating 2 different theories everywhere other than the massless point. Here, even away from the massless point, we have, or rather, here we have a true symmetry where we're not shifting theta by pi, we're coming back to the same theory. Let me just recall some known results for theta equals 0 before getting to the interesting case of theta equals pi. At theta equals 0, if we say turn on both masses with an equal mass deformation, this corresponds to perturbing that C equals 1 CFT by an operator with scaling dimension 1/2. And so one can work out from this a scaling of various quantities. That Vev psi bar psi that we talked about before is going to scale as this mass to the 1/3 power. Similarly, the mass gap would be that mass to the 2/3 power. These things can be worked out, and many of them can be actually seen on the lattice. But like I said, I want to focus instead on theta equals pi, where the phase transition happened before. So let's think about what we know for theta equals pi already. First of all, as we said before, there's going to be a CFT at the origin with m1 equals m2 equals 0, the c equals 1 point. And then we also know that as we take one of the fermion masses very large, we have to come back to the same story we just had before with the one flavor model. So if we say take m2 very large, I'm sorry, the mass label does not show up. This is a plot of m1 versus m2. Sorry about that. So if we take m2 very large, then we should have the same story, whereas we turn on m1, eventually we freeze out these fluctuations between the +1/2 and -1/2 states, and we end up with 2 ground states. And so the gray shaded region here is meant to represent a 2 ground state phase. So we know that we have this, this dashed line, and that roughly 1/3 is going to be where that transition happens for very large masses. And so, intuition and also some work from Coleman back in 1976 might suggest scenario 1, where these lines of c equals 1/2 theories sort of have these hyperbola-shaped connections, and that's the end of the story. The reason you might guess that is that it would seem like if you had an additional flavor of a fermion, it would be easier to fluctuate between the two E equals +1/2 and E equals -1/2. And so you'd freeze out the fluctuations a bit later as you turn on an equal mass deformation. So that's one reason you might guess scenario 1. So there's some recent calculations by Howard Georgi of some correlations of fermion bilinears in these models. And it is suggestive of conformal behavior along this equal mass line. And the suggestion was that the c equals 1 point might actually be extended to a line along the m1 equals m2 direction. This seems to be at odds with the symmetry. So the c equals 1 point we know is the SU2 level 1 WZW model. And all the way along this line, we should have the SU2 flavor symmetry of the two fermions, since there's an equal mass. But the only marginal deformation we can make of that SU2 level 1 model is the change of radius for the compact boson. And that's always going to take us away from the special SU2 self-dual point. So there seems to be no way to keep this a CFT while also preserving the right symmetry that we need. So perhaps something a little bit different is going on, but nevertheless, George's calculations suggest something very interesting happens along that line. And so I'll show you some evidence that what we actually see is scenario 3, where these lines bend opposite the way your intuition might have suggested, and actually meet at the c equals 1 point at the origin. So I'll show you now some evidence from the lattice and some also calculations we can do, strongly suggesting scenario 3 is the phase diagram. I
Depending on the sign of the that's right, exactly. So that's kind of the dimer, yeah. So sorry, dimer. I mean, I think whole scenario 1.
I agree. Certainly, scenario 2 is excluded, and scenario 1, sure, there should be some deformation you can make to flow. I couldn't quite hear. So, and that's a good point. Yeah, so that's the one way you could get around the scenario, except that George's computations show that if it is a CFT, the scaling dimensions of the lowest operator are going to change. So that rules out that case, I think, completely. Sure, quite follow, but in any case, yeah, I agree with you all that scenario 3 is where we should be looking, and I'll show you some evidence now for that from the lattice. Sorry, before the lattice, let me do a quick computation to further suggest scenario 3. So if you take one of the masses very large, we can integrate out the heavy fermion from this action. And what we find is that to leading order, what's left over is the one flavor action plus the shift of the f squared term, because it's minus 1 over the second mass squared. And so the effective coupling is shifted in a similar way. And so this already shows that the phase transition we know from the one flavor model is actually going to be bending the way in scenario 3, where the critical mass is decreasing as we head to smaller masses of the second heavy fermion. So there's one suggestion of this third scenario. Sorry, say that again.
Yeah, there is a G squared in this.
Oh, I'm sorry. Yes, there is supposed to be a G squared here. Yes, thank you for that. Yeah, this is M2 in units of G, or G squared over M squared. Yeah, thanks for that. But indeed, yes. All right, now let me show you the lattice. So here is a plot. The background is the entanglement entropy I was describing for one particular lattice, some large number of sites and small lattice spacing. And so, and this is the kind of quantity we're using, right, to do that same finite size scaling estimate of the location of the critical point in this model. So the background is sort of one of many such pictures we need to make to eventually get these continuum estimates and the black dots of where a critical point is, should one exist. And it also gives us an estimate of the central charge at those points. And what we find is that all along this nice curve following scenario 3, the central charge comes out to 1/2, and we get these this critical line of 2D Ising transitions. And it nicely follows sort of the curve we sort of expected, and is getting very close to meeting along this diagonal line already by a relatively large mass. So furthermore, if we take that expression for the large mass asymptotics that I just wrote on the previous slide, these points, that's the white dashed line. And these points are matching that computation very precisely. Thanks. So everything seems to be checking out here. We match large mass asymptotics, and we see these lines coming together towards the origin, just as in the scenario I was suggesting. So this is encouraging. Let me show you one more encouraging plot from the lattice. Let me explain this. We are here working with open boundary conditions on the lattice. Open boundary conditions are going to explicitly break the symmetry between the two vacua I was speaking about. So if we take the ground state and look at the expectation value just of the electric field, that should be 0 when we're in the symmetry unbroken phase, and should turn on when we go into the symmetry broken phase. And here we have a picture of that seems to match very nicely what we expect. So we again have this this symmetry broken region with boundaries that curve inwards towards the origin and meeting or coming very close to meeting on a line near the origin. So yeah, this is very encouraging in favor of scenario 3, and is heavily reliant on the mass shifted lattice approach I was describing earlier. And so definitely hints towards something very interesting happening near the masses point, as some people have already been suggesting. So let me finish briefly by discussing what happens near the masses point. So we said at theta equals 0, if we do this equal mass deformation, there's going to be a delta equals 1/2 operator returning on, and we can easily see some parallel scalings of these quantities, and it's interesting, but not anything too fancy. So theta equals pi, though, the coefficient of that deformation vanishes. If we take equal masses and set theta equals pi, that operator is not turned on. And so we can ask, what is the deformation here? It's hard to throw all this in the last minute here, but so if we bosonize the fermionic theory, this reveals that there's this massive boson, the Schwinger boson, with a mass that's well known. And then the other bosonic degree of freedom is this compact boson that gives us the SU2 level 1 model. And so we can ask what happens if we integrate out this heavy Schwinger boson and see what happens to just this phi minus field that is giving us the CFT sector. And what we find is this deformation by this cosine operator with coefficient root 8 pi. And it's that point at which this operator in the Sine-Gordon model has dimension 2, is marginally relevant, or excuse me, is marginal with the first order. And so if we think then about the RG flow of the Sine-Gordon model with this particular coefficient in the cosine, This has been worked out, long ago in the 80s by Amit and friends here. And this is describing the BKT transition. And so what we actually end up seeing is that the mass gap, for instance, near the origin should be exponentially small. It should go as e to the minus 1 over that mass squared. This is a nice prediction. It's something that's going to be very difficult to see on the lattice. But what we can look at on the lattice is the correlation length going as the inverse mass gap. It's going to be exponentially large near the origin. And so we can try to see if we can match its behavior and confirm this story of a BKT transition near the origin. And in fact, we can. And so, furthermore, this coefficient appearing exponential can be computed from their RG analysis. And what we can do is extract an estimate of the correlation length from the entanglement entropy that we already were looking at, and see how that correlation length depends on this 1 over m squared. The prediction is that it's exponential, and indeed in this log plot we see exactly this behavior of e to the 1 over m squared dependence. And furthermore, the slope, this dashed line is depicting the value a computed in the RG analysis. Our points seem to be headed right towards that slope and doing better and better as we go to smaller and smaller lattice spaces. So everything is consistent with the story being just this way. So I'll finish there just to sum up. This mass shift drastically improves our numerics and it opens up a larger range of what we can study with Hamiltonian lattice theory for the Schwinger model. And these tensor network methods also are essential to doing really precise numerics and using all these tools. We see this strong evidence for what may be a surprising phase diagram for the two-flavor Schwinger model. So I'll stop there. Thank you.
Great talk. Yeah.
Probably reason something because let's say that we start from n equals 0.
Yeah.
Okay, then we should non-zero value the mass,
Right?
I wonder if there's a additional symmetry associated with mass or not, because if you have a shift, then something going on with this. Right?
That's right. Yeah. So right, you want the symmetry associated with zero mass in the continuum. But right. So on the lattice, if we want to have this symmetry, in order to, you might think you could just shift the sign of this coefficient of the mass term on the lattice. The reason you can't is because of the Gauss law, that for the staggered situation.
In some sense, some interpretation, this is a mass, not exactly as a mass, right? The small a, because it's analog of zero mass, right? What you're doing. I mean, it would be
Well,
yeah. So it's like a definition of what means zero mass.
Well, it's a redefinition on the lattice of what means zero mass. But as you were saying, ultimately we care about the continuum limit as a goes to 0, and so this shift.
Point, especially for two points.
Yeah.
You see that. So people before did not get this properly.
It's
you could charge n to them.
Yeah, for charge.
Yeah,
two,
right. Right.
But one thing that Ross didn't have time to talk about, but if you read the old papers and they developed strong coupling extensions at m lat equals 0, and they all complain that they're really bad, they don't converge to anything. Once you try it at this shifted mass, like it greatly affects strong coupling extension, right? Because strong coupling is large. There you see and it works amazingly well, better than you would expect. So I think even for one flavor. For two flavors, it's a very dramatic because you have this shifted mass. The strong coupling vacuum is highly degenerate at the shifted mass and completely non-degenerate at the unshifted.
But you say, for example, the symmetry is pretty so high.
Yeah.
Right.
Right. Yeah.
Yeah.
Well, it has a symmetry which involves shift of theta by pi, which is you go to a different field. Yeah, yeah. yeah.
Right. Mhm. Yeah, we can talk about either different theories with different values of theta or different vacua or different universes in the same theory with charge n. It's the same idea, right?
So in some of the slide about the derivation of the effective Laplace, so you see the opposite sign as you if you want to be recovered, right?
Right. It's the sign here we care about. Yes. Yeah.
So it's so we can create the scenario and we really
That's very possible. Yeah, I haven't thought about that enough to say either way, but
yeah, they want yeah.
Yeah, we were thinking of adding for farming.
All of this story, but from the point of view of something that I find in the strong popular limit, all these models do exactly what I on the line. And that's exactly yours.
I believe so. Yes, we've thought about some of these reductions in the strong coupling limit. Yeah.
Isolate the electric field, it only takes two values, it takes five.
Right.
It takes five, it only takes two values.
Mhm.
And
Yeah. And yeah, in fact, for in our case, for the two flavor model, we can see that without with the mass shift, we get a 2 to the n degeneracy of the ground state in the strong coupling limit, which
But I think
follows
it's
that.
Heisenberg model, the leading strong coupling limit. Right. I mean, there were some
I mean, for
two flavors.
flavor, yes, I meant for one.
Yeah.
Oh, okay.
And for my-
I see. Yeah, I can describe briefly. What we do is integrate out the gauge field, so we just have a non-local Hamiltonian coupling, a spin chain for these fermion sites, and then we use a matrix product state ansatz, minimized to extract this ground state. Yeah, it's a one-dimensional. Right, exactly. Yeah, sort of the canonical case.
It's not necessarily good at the one. It's a whole.
That's-
Are you really sure about
It's a good point. Yeah. So right, DMRG is ideal when you have a finite mass gap and not so much at the critical points. The nice thing about this, I mean, many things can be said, but one thing is that when we do these finite size scaling analyses to get these critical points, this is not exactly where the mass gap goes to zero. We're sort of approaching that point, but on the finite lattice, before we think about the continuum extrapolation, is there still a finite mass gap? And so we expect the convergence to be just fine. That's also true. And that may be related. Yeah. I mean, all of these points, right? There should be a zero mass gap, and so we'd worry about this. But it may be that as we go towards the origin, we somehow need to get closer to that gapless point to really estimate. So that might be part of the problem.
Yeah, so that's part of the correlation.
Say that again. Sorry.
How's the correlation that scale?
Right. Yeah. So this is all. This is, for instance, a bond dimension of 600 that makes this plot, but we've checked that it changes very little if we take it to 1200. It seems to be well converged. You might worry that we saturate the entropy you could get from the MPS ansatz, but we're not in that regime, so we're safe there.
Yeah, certainly the width of this region becomes extremely narrow. So the only option is it would be exponentially small, or you're gonna have increase in some functions. not, let's think about it together.
Then,
Yeah, so we'll have a break and we
we reconvene at 3:50.
yeah, like have a